Hello everyone. Today we're going to be talking about the mass and the energy of objects traveling at relativistic speeds. It turns out that mass and energy don't behave exactly the way that we'd expect them to in classical physics. But by now you're probably used to that sort of thing. Now we know that as an object approaches the speed of light, its mass approaches infinity. This is a consequence of mass dilation, which we've just been learning about. But this has interesting consequences for the acceleration of an object. Can you remember Newton's second law? Newton's second law says that the acceleration that an object experiences is proportional to the force applied to it, but inversely proportional to the mass. So when the object becomes more and more massive, if we're still applying the same force, then we get less and less acceleration coming out of it. That means the closer we get to the speed of light, the harder it is to speed up. So if the object could ever actually reach the speed of light, which is impossible because we don't have enough energy to do that, then it would become infinitely heavy, right? This means that just before it reaches the speed of light, the amount of force that you have to apply to make it go faster is impossibly large. There's nothing in the universe that can generate this much force. And so the object becomes just about impossible to accelerate. We can also get to some interesting consequences with the gravitational field of that object, but that's not really covered in this course. It's more in the realm of general relativity, which deals with acceleration and gravitational fields. In Year 12, we only need to know about special relativity. That is, the special case where we're not accelerating. Now, the speed of light is sort of a maximum speed of all known matter. And we can see this because of mass dilation, right? We can see here a photograph of a speed limit sign that used to exist in some places in Australia. It's an unlimited speed limit. It means that you can go however fast you want, and it's impossible to be arrested, unless of course you hit something. However, even if there was no maximum speed limit on the roads, the speed of a car would still be physically limited by the speed of light. There's no way that any object can travel that fast. We know that it's impossible to make an object that's already stopped go slower, right? If we try to slow it down anymore, it'll just start speeding up again in the other direction. We also know that if you try to make something colder than absolute zero, it can't happen. All the particles in the object have already stopped vibrating, and so you can't get any colder than absolute zero in temperature. In the same way, you can't get any faster than the speed of light in speed. It's a hard limit. There's no way to bypass it. In the same way that you can't get any slower than stopped, you can't get any faster than light speed. It turns out that if you can get faster than light speed, then due to how we understand time working, it's possible to make things happen before the event that causes them to happen. This is called the breaking of causality, and it's one of the main reasons that people believe that faster than light travel is impossible. But the problem is, we can still add energy to objects that are moving fast, right? We can give them a push or something, and that'll presumably increase their energy. And if their kinetic energy increases, surely that means that their velocity must be increasing a little bit. So the object can't really gain speed is the problem, but it still has to gain energy in some form or another. And so what happens is that it gains mass. It means that if we put energy onto a moving object to try and make it go faster, instead of getting faster, it'll get heavier, right? So what Einstein realized when I was working on relativity, is that energy and mass are kind of the same thing. All objects will have a rest energy. Now, rest energy consists of the mass that they have even when they're not moving. And presumably, if we're clever enough, we can figure out a way to turn this mass back into energy, or put energy into an object to turn it into mass. So an object's total energy, that is, its rest energy plus its kinetic energy, is given by this equation here. E equals m0c squared over our familiar factor. Now, this doesn't look very much like our equation for kinetic energy yet, but we'll get to that in a moment. So when the object is at rest and the gamma factor is exactly 1, we can see that the rest energy of the object is just going to be equal to mc squared. And there we have the famous equation that you've probably all known about for a while. Now, bear in mind that we have a factor here of c squared. That means that if we get a very, very large amount of energy and we want to equate it to m, we have to divide that energy by c squared to see how much mass we gain. Now, we know that c is a very large number, right? 3 times 10 to the 8. C squared is going to be an even larger number, 9 times 10 to the 16. So once we divide our energy by that, we're going to end up with almost no mass. So even a huge amount of energy only produces a very, very small amount of mass. So we can think of mass as an extremely compressed form of energy. If we take energy and we put it so close together that it becomes actual physical matter, then we have a tiny bit of mass. Similarly, if we can take a tiny, tiny bit of matter and turn it back into energy, we'll end up with an enormous amount of energy. So the kinetic energy, Ek, of the object is the difference between its total energy and its rest energy. Now, the total energy we already have an equation for, and the rest energy is mc squared. So we end up with this equation here, which doesn't look very much like our original equation for kinetic energy, to be perfectly honest. To find the reason why this changes into the equation that we know, we need to know a bit of advanced mathematics called the Taylor series. Now, I won't go too much into it. The idea of it is that 1 over the square root of 1 minus x squared can be expressed as an infinite series that starts off with 1 plus half x squared plus something like 3/8 x to the 4 plus 5 to the 16th x to the 6, and we continue on in this pattern with x getting a higher index each time. Now, if we were to replace this with the Taylor series expansion, then that means that this whole x to the 4, x to the 6 would get extremely small as each time we get x, we're taking v over c, and that's already a very small number. It means that we can start ignoring these higher order terms. And the mc squared that's multiplied by 1 is removed by this mc squared. So what we end up with is an equation for kinetic energy that looks something like the m0c squared times half of v squared on c squared. Starting to look familiar now. The c squared cancels out, and we end up with half mv squared, which is exactly what Newton observed. So, when V is very, very small, this value will end up looking very, very much like this value. If you want to check that, try it out on your calculator. Put in a very, very small number for V over C, so maybe something like 100 meters per second for V, and 3 times 10 to the 8 meters per second for C. Substitute all this in, and you'll end up with a value for kinetic energy. Then do the same calculation with this. I can guarantee that if V is small enough, you'll end up with a kinetic energy that is pretty much identical no matter how you calculate it. So mass can be converted into energy, right? We've just learned that if we put energy onto a moving object, it will turn into that object's mass. But it turns out that mass can be converted back into energy. And we can do this by causing atomic nuclei to interact together in specific ways. And this is more in the realm of nuclear physics. Nuclear referring to the nucleus of the atom. So this nuclear radiation, the energy that's produced by these reactions, is used in power plants or in weapons of mass destruction in order to release huge amounts of energy in both cases. Because C is very, very large, the change in mass only needs to be very, very, very small to get a large amount of energy. This means that even if we only have a small amount of nuclear fuel, we can produce a larger amount of energy than if we were to just chemically burn the same amount of chemical fuel. So this is the end of the theory. We've learned a bit about how mass and energy relate to each other and how we calculate kinetic energy in relativistic physics. Let's go on to some questions. What is the rest energy of a gram of hydrogen? Can you remember our equation for the rest energy? It's just E equals mc squared. So it turns out that if we take 1 gram of hydrogen and we burn it in air, we end up releasing 140 kilojoules. It turns out that if we have a single gram of hydrogen, it ends up being about 11 liters. So this is our heat of combustion if we're chemists. However, we're not chemists, we're nuclear physicists now. So to figure out the rest energy, we need to be using E equals mc squared. Let's look at some of the numbers a bit further down. 10,000 kilojoules. Now it turns out that this is pretty close to the recommended daily intake for a human being. So over one day, your body turns food into this amount of energy. It's quite a fair amount of energy. It'll get you through your entire day, right? Our next option is 1,000 times more than this. So it's more energy than your body processes in 2.5 years. This is in fact the energy yield of the most powerful non-nuclear bomb in the world. So this amount of energy could destroy a few buildings. Our last option is 90 billion kilojoules. And if we use E equals mc squared, and we're right in the SI units we use, we'll end up with 9 times, what is that? 10 to the 13 joules? Or, taking 3 zeros off, 9 times 10 to the 10 kilojoules. So this is the energy contained in 1 gram of hydrogen, the hydrogen's rest energy. If we could suddenly remove all that hydrogen from the universe, and have all of its mass turned into energy, we would release this much energy, which is about equal to the yield of a nuclear bomb. Question 12. Given that the units on each side of an equation must be equal, find an expression for 1 joule. Now, to answer this question, we can use any equation that uses energy. We could use E equals mc squared, or we could use our equation for gravitational potential energy, or we could use our equation for kinetic energy. The other thing we could do is figure out an equation in terms of force for energy, that is, E equals Ft, and then simply use E over d to replace the F in F equals ma, or F equals P over T. Now, for all of these, you're going to end up with kilograms. We use E equals mc squared. We can see that the mass is measured in kilograms. C squared is going to be meters per second, all squared. So that gives us meters squared per second squared. If you like, you can work that out for all the rest of these. But no matter how you do it, you'll always get this answer for the units of energy: kilograms, meters squared per second squared. So why don't we measure energy in kilograms meters squared per second squared? Well, because we've got an easier way of saying that. We just call it 1 joule. Question 13. A milligram of hydrogen collides with a milligram of anti-hydrogen. Assuming the mass of both is converted entirely into energy, find the amount of energy released by this antimatter reaction. Anti-hydrogen is an exotic form of matter that we call antimatter. Instead of being made up of positive protons and negative neutrons, it's made up of negative antiprotons and positive anti-electrons, or positrons. So this gives it some very unusual qualities, one of which is that if it comes into contact with regular hydrogen, both the anti-hydrogen and the regular hydrogen are completely annihilated. They're wiped from the universe, and then all of their mass turns completely into energy. So, how much energy is released? Bear in mind that a milligram of anti-hydrogen is more anti-hydrogen that has ever been produced in the world, by a factor of several hundred. So, we use E equals mc squared to figure this out. Now, we're given a measurement in milligrams, not kilograms, which is annoying because we're always meant to use SI units for equations like this. Remember that 1 joule is a kilogram meter squared per second squared, not a milligram meter squared per second squared. So how many milligrams are in a kilogram? Well, there are 1,000 grams in a kilogram and 1,000 milligrams in a gram. So in 1 kilogram, there's 1,000 times 1,000 milligrams. That is 10 to the 6. So 1 milligram is 10 to the minus 6 kilograms. Substituting in our 2 milligrams, one of hydrogen and one of anti-hydrogen, we have 2 milligrams times the speed of light squared. Using a calculator, this evaluates to 1.8 times 10 to the 11 joules. If we were to write that out, it would look more like 180 million kilojoules. This is a lot of energy. Question 14. In chemistry, if we burn 46.1 grams of ethanol, which, as you know, we sometimes use for fueling cars, we get a little over 1,000 kilojoules of energy out. Fair enough, right? Nice and renewable. But we're physicists, not chemists. So we want to find a way to convert all of the ethanol's mass into energy. Maybe by turning half of it into antimatter or something. So we want to find the rest mass of this amount of ethanol. So we use E equals mc squared. M is the mass here, and c squared is the speed of light squared. Of course, we're given this in grams, so we need to convert it into kilograms. If you're a chemistry student, you might recognize this as the molar mass of ethanol. So this is 1 mole of ethanol. Chemists often use grams in order to measure certain quantities of chemicals. It makes it more convenient. So, substituting in our mass and our speed of light, and converting, of course, the grams to kilograms, we end up with an answer of 4.149 times 10 to the 15 joules. Except it's kind of hard to compare this to our number of kilojoules because the units are different. So we'll convert this to kilojoules and maybe write out all the zeros. As you can see, we get a very, very large number. We get something like a billion, a trillion times more energy if we can convert all the mass to energy than if we just burn it chemically. Of course, in a nuclear power plant or something like that, we can't convert all the mass into energy. We can only convert something like 1/1,000,000th or even 1/1,000,000,000th of its energy. So let's divide that by 1,000,000. We're still getting far more energy out of our nuclear reaction than we are out of our chemical reaction. And this is why nuclear power plants are able to produce so much power. Question 15. When a spaceship is traveling at almost the speed of light, what happens when it tries to speed up? Now, obviously, if we look at it from inside the spaceship, everything's going to be working exactly as normal, right? The principle of relativity states that he can't notice that anything's off. But what about from outside? What about looking at the spaceship in a frame of reference where the spaceship is moving at almost the speed of light, instead of being at rest? Well, the relativistic mass will be huge, right? So if we try to accelerate it faster, and we apply a force to it, the acceleration produced won't be very big, and it will get smaller and smaller as the speed of the spaceship gets closer and closer to the speed of light. If we could ever reach the speed of light, then the acceleration of the ship would be zero, no matter how much force we applied. And additionally, most of the energy produced by the rockets will be turned into mass, right? E equals mc squared shows that if we try to put energy onto a moving object, it'll instead turn into mass. And so both of these sort of combine together to say that you can't get to the speed of light, don't be silly. If you're at the speed of light and you try to speed up, you won't get faster, you'll just get heavier. So this is the end of the questions, which means that we're at the end of the lesson. So in this section, we've learned a bit about the relationship between mass and energy, and we've looked at how we measure kinetic energy in relativistic physics, and how it changes for classical energy. The next lesson will be our last one in this module. We'll be learning about space travel in the far-flung future, where we might have to worry about relativistic effects.